Hello everybody. I have another USB charger for us to take a look at here. This is again a bit of a fill because I'm currently working a more complicated project which I've had to order parts in for, so that can't come out this week, so we'll take a look at this instead. This is a random charger. I can't remember how much I paid for it, not much, probably less than £3 or £4 off of AliExpress as usual. I've had this in my pile for a few months now, just waiting for a time like this when I need to get something out quickly. This is an interesting charger on account of the fact it has 8 USB ports on the back of it, this rather attractive flower on the end, and interestingly a Korean plug, not a European plug. I think the difference is the pin spacing or pin diameters are slightly different, but I'm not sure. They look very similar. This one is supposedly Quick Charge 3, and I think this might actually be the first charger we've taken apart here which genuinely is Quick Charge from my preliminary testing. If we have a look at the markings on it, it is model BK1319. The input is 220 to 240 volts, 50-60 Hz, 0.5 amps. That's interesting. Usually chargers like this would be a universal 100 volts to 240. You do get some that aren't, so I'm not saying that's strange, but what is unusual is that it's 60 Hz at 230 volts. And I was racking my brains trying to think, is this a typo or is there a country where this is a standard? And I think, if my memory doesn't fail me, Brazil uses 120 and 230 volts in different regions of the country, but both of them are 60 Hz. So I'm guessing that's probably what this is for. I think Brazil also used the European Schuko plugs, but again I'm not 100% sure. I need to check that. I'll put it on the screen. In terms of outputs, there are two different ones listed. There is the output 1, which is 5 volts 3 amp, 9 volts 2 amp, and 12 volts 1.7 amp, which is the quick charge output. And then we have the other ports are, I'm going to assume this is a combination of 2.4 amps maximum. So let's give this a test. 1 second, I need to get my hoppy. So I have the hoppy set up here. I'm in the 2.4 amp port for starters. This is not an ideal setup. As you can see, I've had to remove the USB-A plug from my test load because this is broken. The pins inside it have snapped off, so I can't connect to it anymore. And I'm in fact building a replacement test load at the moment. Hopefully the project's a bit stuck at the moment, but that is beside the point. What I have is a USB-A to C cable feeding my USB-C test load, which is then connected to the USB-C port on my test load here. I have 5 volts currently coming out of the port, and we'll start loading that down and see what happens. It's 150 milliamps, 200 milliamps, 300, 400. This is supposed to be a 2.4 amp port. 500 milliamps and it's still fine. 700, 800, 900. That's 1 amp, and the voltage is still fine. We'll keep going. 1.2, 1.3, 1.4, 1.5, 1.6. The voltage is starting to drop off there. 1.8, 1.9. 2 amps, and that's the fan come on the test load. The voltage is still acceptable, so we'll keep going. 2.3 amps, and the voltage is dropping further, but it's still acceptable. And it would appear I've maxed out my test load at 2.379 amps. And the voltage, I see the voltage there has plummeted way off. 3.6 volts, so we'll start backing that off. 3.9 volts, 4 volts. So that's it. At its acceptable voltage is about, oh, there we go, 2.41 amps ish. So this would appear to be legitimate that it can actually provide that amount of current. I'm going to leave this to run for a while and we'll see how hot the power supply gets. If we have a look on the hoppy here, with the full load of just over 10 watts, nearly 11 watts, it's drawing 15 watts out the grid, so we're losing, well, it's that, just under 3 watts in here. So this will probably get mildly warm, not too hot. Power factor is 0.5, which is pretty crap, but that's normal-ish. Yeah, I'm going to leave this to run for a while and we'll see how warm the power supply gets, so one moment. Yeah, so that's been going for about 15 minutes, at which point my test load started to complain it was overheating, and the power supply is mildly warm to the touch, but I wouldn't exactly call it hot. Anyway, I have let the test load cool off a bit, and I have changed now over to the quick charge port. This one is supposed to be good for 3 amps, so preliminary testing has showed that it actually is good for a higher current. I'll show you now though. Again, same setup as before, meter, test load, connected. If we start increasing the current draw, it's 0.1 amp, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, the voltage is dropping, and that's 1 amp, and the voltage has dropped off to 4.8. We'll keep going, up 1.3 amp, 1.5 amps, 1.6, 1.7, 1.8, 1.9, and 2 amps, 2.1, 2.2, 2.3, 2.4. This is where the previous one crapped out. The voltage on this one has dropped down to 4.6, which is the lowest voltage, technically speaking, you can consider acceptable. But we can keep going. The previous one, the voltage just dropped straight down to basically 0 when I tried to continue past this point. Oh, wrong way. If we continue increasing the load, that's 2.5 amp, 2.6 amp, 2.7 amp, 2.8 amp, 2.9 amp, and 3 amps there. The voltage has dropped down to 4.5 volts, but that's largely because this cable I'm using is a piece of crap and has aluminium conductors and is getting really quite warm. So I suspect if you used a less shit cable, the volt drop would be within specification at 3 amps draw. Again, if we go back to here, we are taking 13.8 watts, so let's call that 14 watts out, 18 watts in, power factor of 0.5 again. That means we're dropping again about 4 watts in here, so I'm not expecting this is going to get hot, but I'm going to let it run for a while and we'll see, so I'll be back in a second. This is a bit harder to show because I've had to use back to my type A meter, but this is legitimately QC3. It would appear I have an old phone here which supports the QC3 protocol, and when I plug this in and actually manage to get it to make a connection, it would appear, there we go, you can see it draws half an amp at 5 volts and then negotiates up to 9 volts. So this does legitimately appear to be a quick charge charger. I don't have anything that can trigger it to 12 volts. I don't have a trigger board on hand set up for that, and this phone doesn't support 12 volt charging. But you can see there the signal on the data lines, and it has gone up to 9 volts on the screen. It's drawing 700 milliamps at 9 volts. So this is legitimately a quick charge charger. So from initial testing, this one seems as though it might not actually be as bad as some of them are. The claims on the ratings appear to be legitimate. It doesn't overheat massively. It has a somewhat excessive number of ports, I would have said, especially given that these are all paralleled, as best as I can tell, because you cannot load them, multiple of them, to 2.4 amps at the same time. But I suppose if you wanted to charge a phone on the quick charge port and then you had a bunch of smaller devices you want to charge at low current, maybe it could work. most newer phones, I tried it with my new phone, which supports power delivery, and it will not use the quick charge functionality. It just charges on 5 volts. So I'm not sure how useful this would be with a modern device. Anyway, in terms of how to get this open, usually one of the ends will pop off, and I don't see a seam around the bottom here. There is one around the top, but I can't get my nail into it, which you usually would be able to. So I figure we'll just try prying with a screwdriver and see if that can get us anywhere. Nope, it is not going to. Okay, I'm going to take a few minutes and see if I can brute force this open. I'm going to have to get a saw and cut it, but I will be back momentarily. Well, that was surprisingly difficult, although that is a good thing. With these, it is supposed to be only possible to open them with a tool, and in this case that was definitely true. With some of them you can just pull them apart by hand, so that means you can't accidentally get access to live parts if you, say, pull it out the plug and the case falls apart. If we get the board out here, maybe I should have thought ahead as to how to do this rather than pressing record before I had something to pull it with. Can I get it out? No, I can't. 1 second. Okay, so board extracted, and my initial instinct is I am very impressed. This is extremely good. So, starting off, we have a fuse, which is rare. We have an interference suppression inductor, and we even have a bit of card, like plastic card, inserted here to stop the incoming mains terminals from touching the inductors behind that. That looks like more interference suppression inductors, maybe. We then have 2 transformers. We have, it looks like, 2 driving chips, an optical isolator for the communication back. We have 2 interference suppression capacitors, which are, when I see them, actually interference suppression capacitors. They're not 1 kV ones, they're properly tested and rated. We have 2 synchronous rectifiers on the output. This here will be the circuitry communicating back. That output smoothing capacitors look a little bit small for my liking, but that's not a huge problem. We have all of the ports here, and then this is the other one. We have, if we look on the bottom, we have a very nice isolation gap here. There is even legs on the transformers in order to keep the secondaries distant from the increasing isolation gap. Looking at the secondary on this one here, you can see that it is properly insulated on both of them. They're actually properly insulated, so you're not going to have any issues with the isolation of the transformer being poor. These really actually seem quite good. I'm very surprised. I'm looking for things to complain about and I don't see anything. As I suspected, all these ports do appear to be in parallel, except this one, which is not overly surprising. I was expecting that. Even the soldering on this looks fairly good. These power supplies, what do they share? They share the bridge rectifier tucked in there, and the interference and the fuse, and other than that I don't think these share anything. I'm going to take a minute and see if I can reverse engineer this, because it looks surprisingly complicated and I want to see what all this interference suppression circuitry is. And my camera battery is going flat, so 1 moment. So here is my, I'll call it partial reverse engineering. I've omitted certain parts of the circuitry here which I figured were not important and would just overly clutter things. So there's some stuff missing, but it's not important. Basically, this is 2 chargers in one. They share very little. They share the fuse, the choke, the rectifier, and that's about it. They don't share anything else. Going through this here, I'll explain briefly what we have. We have the simpler one and the more complicated one. The top part here, so ignore all this for now. We have incoming mains go through the fuse, through the common mode suppression choke. So we have on the board here fuse and common mode suppression choke. then goes into the bridge rectifier, which is tucked down in there. We then go on to one of the smoothing capacitors, which is that one there. That is the DC smoothing capacitor for this supply. The driver chip, which is that driver chip there, that one is a QC5883. I have looked for a datasheet, I can't find one. I'm not saying there isn't one, but at least when I had a look, I couldn't find it. I could find references to the sheet, and I found a few suppliers going, see the datasheet, but the link they pointed to was dead. It led to 404, page not found. We have then the transformer here, which is this transformer. There are 3 windings on it: the primary winding, the feedback winding, and the secondary winding. The primary and feedback windings are both on the primary side. So the primary winding is the one that the chip actually drives in order to power the device. The feedback winding is a low voltage supply, but reference to the mains. So that gives you a FELV, functional low voltage supply, on the output here. So Schottky rectifying diode and a, 4.7 microfarad smoothing capacitor here. There is a resistive divider which feeds back into it, and this is how it estimates the output voltage. It doesn't give you a very accurate representation of what the actual output is on this winding here, but it works well enough. It's fairly common, they do that in order to save cost. We have, what else do we have on the primary side? Not much, because I've removed. There is a snubber network on the primary coil here, but that is not shown for simplicity's sake. The other winding here, the secondary winding, that is the self-supply separated extra low voltage, or safety extra low voltage, depending you ask. There is a capacitor here which links between there and there, but again I didn't put that in to make it neater. This chip here on the output, the MT6704, is a synchronous rectifier, which is basically a MOSFET with a microcontroller strapped to it that acts as an ideal diode. That then has a 680 microfarad smoothing capacitor on the output, and that feeds the 8 USB-A ports here, all the green ones, which I have not drawn here again for simplicity. On the other side, we have a differential mode suppression choke, which is that thing there. Don't know if you can see it properly or not, but that thing there in between the two capacitors. We have another 18 microfarad smoothing capacitor, which is this one here. They share the same 0 volt reference, which is the ground. So again, for simplicity, I haven't drawn in the connections. The driver chip for this side, which is that driver chip down there, I don't know if you can see it properly, but that is a QC3579. Again, I had a look, I can find references to it, I can't find an actual data sheet, but it is a more complicated driver chip. We again have a transformer, which is this transformer this time over here. This one, again, 3 windings. We have the primary winding, the feedback winding, and secondary winding. This one does not use the feedback winding for its voltage regulation. That is just to power up the control circuitry within the driver chip here. It instead uses a more accurate voltage feedback using this optical isolator. What we have is, so the primary is fed directly on both of these from the positive rail and is then switched to the 0 volt through the built-in MOSFETs. I'm assuming they'll be in these. We then have, as I said, rectification, another 4.7 microfarad smoothing on the feedback. On the other side, again, there is a interference suppression capacitor, which I haven't drawn, which is in there, the blue thing. That we have on the other side another MT6704 synchronous rectifier on the output, and we have another chip up here. It is not marked at all, I have no idea what it is, but what it is a port driver. So this takes the data lines from the USB-A port for the quick charge, which is this one here. That is the tiny little 6-pin chip, I don't know if you can make it out, behind this smoothing capacitor. It takes the data lines from here and does the communication with the device in order to negotiate a voltage, and then it will drive through this here, through Q1, which is that tiny little transistor in there, again I don't know if you can make it out, and a 2.2k resistor, the LED in the optocoupler, which is this 4-pin package here next to the interference suppression capacitors. What an optocoupler is basically a, well, it's in the name, optical coupler. It has a infrared LED on one side, which you turn on and off, and then on the other side it has a phototransistor, which is turned on by the light from the infrared LED. So the infrared LED gets turned on, and that allows current flow through this transistor on the other side, which you can use to then signal or pass a signal from one side to the other without electrically connecting the two circuits. So this one here is, I think, 8 kV rated. So you could put 8,000 volts between here and it's not going to conduct through, but you can pass the signal between the two sides. There is a small capacitor for stabilization, I'm assuming. I can't work out what value it is because I'm not taking it off the board. And then that feeds into pin 3 of the driver chip, which will be giving a data communication, I'm assuming, between this chip and this chip, which allows them to vary the output voltage on the secondary by sort of communicating and varying the switching on the output. I could hook scopes up to this and stuff and show you, but I can't really be bothered going through all the faff of that. On the output here, there is also, I should mention, a blue LED which is powered off of the quick charge side, but again I didn't draw that for simplicity. And the smoothing capacitor is a different one. It is this one here, which is 470 microfarad, 16 volt rated, I think polymer capacitor probably. I don't love that because a 16 volt capacitor I personally wouldn't want to charge to more than 8 volts because I generally don't like charging them more than half. So for a 12 volt output, which this could be, I would have preferred a 25 volt rated capacitor, but that's being picky. It will be fine, it just might have a slightly shorter life. As I said, I have omitted most of the snubber circuitry and stuff from the primary side for simplicity, but that's not important to the functionality of the device. So at this point I would normally desolder these transformers and take them apart and show you the internals of them. But in this case I'm not going to do that because I actually quite like this module and I'm going to probably repurpose it for something eventually, and I don't want to destroy it. And also I can tell you just by looking at them that these transformers will both be properly isolated, because if you look carefully, it might be hard to see on the camera, but both of the secondaries are not enamelled copper wire. They are in fact triple insulated wire. So I can guarantee the separation will be fine in these, and the separation distance is more than satisfactory on the PCB. The components are all real. Overall this seems like a actually well designed and built power supply. It does leave me to question somewhat then how it is that these have ended up on AliExpress for like 2-3 quid, because I can guarantee you this board cost more than that to manufacture just in parts. So something has clearly happened at some point that's made these get rejected, but I can't see any safety issues with them, just from the testing I've done. They have proper interference. They have more interference than even some of the high quality supplies that I've seen, branded ones. Common mode and differential mode. They have the appropriate capacitors. They have proper isolation, properly constructed transformers with extended legs in order to increase the isolation distance. One thing I did notice with this, which is a little bit strange, is for some reason the primary winding on this transformer here, normally you have the pins all next to each other in line, and there are 1, 2, 3, 4 pins on the primary side of this transformer, which usually would be primary A, primary B, feedback A, feedback B, and then on the output you would have secondary A and secondary B. But if you can make it out, this pin here is not actually connected to anything. It's not solid, it's just sitting through a hole in free space. And this pin is the other end of the primary. I don't really understand why they've done that. It seems rather strange to me, because if you didn't do that, you would have a much greater isolation distance. It means that your primary is here and your secondary comes out here. That is why they've had to add this additional leg in order to increase that distance, otherwise the isolation would not be possible between these two pins. It seems strange. I don't really understand their logic in having done that. There probably is some reason for it. I'm guessing something to do with manufacturing. This other transformer here is much more as you would expect. We have two pins on the output for the secondary, and then the primary and feedback here on the other side, and a big gap in the middle. One other thing I have noticed is there is this trace here, which doesn't do anything. And if they removed that, you would have a better isolation distance between here and here. But again, that's nitpicky because this is more than sufficient. I'm not clear. There are a few what I would term as design errors on this board that I noticed when I was reverse engineering it. Especially up here. These resistors don't connect to anything. So there's a bank of resistors that are connected on one end to the 0 volt, and the other end of them just doesn't connect to anything at all. So I'm not sure what those are for. And there were a few other places where there were pads and traces that seemed to connect nothing to nothing, or be connecting parts that are unnecessary or don't make sense. So that might be why they've rejected these. This is, if you see here, revision 1.0. Maybe that's why. Maybe these were prototype boards. I'm not sure. But they do seem legitimately to be fairly good. The other thing it could always be, as I said previously, is that the USB-A quick charge is not really a thing anymore. So perhaps these boards were properly manufactured and they just wanted to get rid of them. It does seem a bit strange to have quite so many ports on one charger as well. 7 ports with a 2.4 amp combined total supply out seems a bit unusual, because you're not going to be able to charge 7 large devices off this. I can't even think really why you'd want to charge 7 devices simultaneously. Maybe for some sort of commercial application. I have seen much larger units than this, which are 19-inch rack mount, intended for in institutions like schools and universities and so on, where they have a big trolley or a rack with lots of laptops in it for people to use. They sometimes will have a huge big 19-inch rack mount USB-C power supply with 10 or 20 power delivery USB 120 watt outputs on it. So it might be for some sort of application like that. But yeah, this overall seems like a fairly good device. I'm impressed with it, and I'm going to put it in my pile of stuff and probably reuse it for something eventually. I will stress before I end this that just because this one is fine does not necessarily mean that they all are. Most cheap power supplies you'll buy from eBay, AliExpress, Amazon, wherever, will be low quality, dangerous, substandard shite, and you're going to be risking electrocution, fires, problems, blowing up devices, putting mains out the output, all this kind of thing. So I would not advise buying them. This very specific module actually seems good, but I'm very surprised by that. Yes, with that sort of disclaimer out of the way, thank you very much for watching, and I will see you in the next one.